Hello everyone. Before my video starts, I just want to let you know that you should subscribe and like because this took me a very long time. Anyways, I hope you enjoyed the video. Now on to the video. Have you ever wondered how a computer works? You know what? You probably haven't. But if you have, here's a simple guide to understanding the CPU. Before we begin, let me clarify. This video won't be covering everything about how a computer works. Instead, it focuses on the CPU in an oversimplified way. If you're looking for a more in-depth explanation of an entire computer system, I recommend checking out a different video. Alright, let's get started. What is the CPU? The CPU, or Central Processing Unit, is often called the brain of the computer. But just like your brain relies on the rest of your body to function, the CPU needs other components to operate efficiently. These include RAM, storage, like SSDs, and the GPU, which is responsible for handling complex graphical tasks. What does the CPU do? The CPU manages most of the processing tasks in your computer. It handles logical operations, runs programs, and coordinates activities across its multiple cores. For gaming or graphic intensive tasks, the GPU takes care of rendering visuals, while the CPU focuses on logic and other computations happening behind the scenes. Anyways, now that the introduction is done, it's time for us to actually get to the juice of how a CPU works. The CPU does a pretty simple job. It may seem like it does a lot of work, but it all boils down to this pretty simple execution cycle. It's called the fetch, decode, execute. The CPU operates like this. Let's say if you have a program. This program usually gets fed into a compiler, but we're not going to explain that in this episode. Instead, the program is made of ones and zeros. But in reality, a program is made up of a simple thing: machine code. Machine code is, well, machine code. It's a type of code that your CPU actually understands, because you can't walk up to it and start spouting out the C++ and expect it to know what you mean. Instead, the compiler converts that into machine code, which the CPU knows how to process. Most instructions are made up like this. There's an opcode and operands. The opcode is, well, something like this. Every instruction has an opcode, and a lot of them have operands. You can say an object, and then, well, an object, the name of it is its opcode, and the properties about it are its operands. You can think of it kind of like that. All of these instructions get executed by the fetch, decode, execute cycle. Now let's go for it first. First, the CPU fetches it. By this, it gets a line of code, the first little bit of it. It knows how to get this based on a whole bunch of other logic that we're not going to discuss right now. After it gets it, it's time for the decode cycle. This is the stage where the instruction is decoded, meaning the CPU figures out what needs to be done with it. Now it's time for the execute cycle. We're not really going to discuss right now how the CPU executes things, but once the instruction has been fetched and decoded, it gets plopped into the CPU and does some internal things and executes it. This could be a multitude of things, from setting a singular bit in memory all the way to playing a massive video game, but that's made of millions of lines of code. And that is how the fetch, decode, execute cycle works. But that's just a broad little thing. So let's go deeper, even closer, down to the transistor level. If we look at this little diagram of the CPU, it's actually pretty simple. Most modern CPUs work on a thing that kind of looks like this, where there's a control unit, an ALU, and registers. But most modern CPUs have a lot more than just that. When an instruction is fed into the CPU, the control unit takes it and does its thing by converting it into a whole bunch of little control lines, signals. Because the control unit knows what this means, but the ALU and registers do not. So let's say we wanted to place the number 5 into register A. Well, 5 in binary is 0101. And so this goes to place. So once it goes to place it in there, it kind of doesn't really like this. So according to the opcode and its operand, the operand needs to be placed into the A register. Therefore, well, that's what it's going to do. The control unit converts this into a few little pulses, the first 5 on the bus, we're not going. The control unit converts this into a few little pulses and places that 5 of the bus. We're not going to discuss what that is right now, but then stores whatever is on the bus onto the A register afterwards. It is done by executing that thing. That's usually how a CPU works. But there are still a lot more things that we could discuss, like, yeah, sure, it's a control unit, and ALU and registers. How do those things work? Now, I have no idea how the control unit works. So, hello, I'm sorry to interrupt the video, but this is Future Rowan, and I want to tell you, you should subscribe and like, because this took me a very long time. And that's actually my only reason. Anyways, continue the video. Just look at these two today. Anyways, let's go deeper. Even deeper. If we look right here, this is a transistor. It may seem like literally nothing, but this is the building block of a computer. Every single last thing is made of these little dudes. All of them work together to make logic gates. One of the simplest two logic gates is the NOT and the AND gate. They work like this. If you take the NOT gate and input a 1 into it, it outputs a 0, and vice versa. It inverts everything that comes into it, while the AND gate works a little bit differently. It has 2 inputs instead of 1, but that still has one output. And the only time this output is ever on is when both of its inputs are on. We can make literally anything with these logic gates. In fact, that's already what's been done inside of your computer. The CPU is made of hundreds of thousands of millions of these, sometimes even billions of them. And all of them work synchronously in order to build things. But let's look at this. How do you go from typical logic gates made of transistors to adding numbers together? Well, let's look at it like this. Adding numbers together takes, well, not very many things. You need to know how to add, and you need to be able to do that. But a computer doesn't know any of this, so we have to figure it out in binary. Let's say we want to add Let's say we wanted to add 1101 to 0011. Well, that'd be done like this. First, let's take our first 2 digits. Well, what is 1 plus 1? Well, obviously that's 2. But what is 2 in binary? Well, that would be 10. Afterwards, what do? Well, we carry the 0 and carry the 1 over to the next place. Mainly because we can't have 2 digits in one place. Okay, so it's now time for the second part. Now it's 1 plus 1 again. Do the same thing, carry it over. Now it's to go to the third place. Oh my god! What is that? 1 plus 1 again. Do the same thing, carry it over. But now at the final step, it's 1 plus literally nothing. So we put the 1 down. So we have successfully gotten 10000. Okay, so that's how that works. But what do we do all this for? How can a computer do that? Well, like this. Let's look at the logic gates again. We can build things out of them, right? So let's take a singular AND gate and hook its output up to a NOT gate. Now we smoosh that into one little package, and then, oh my god, a new challenger has approached. It's the NAND gate. What do we do with it? Well, the NAND gate is actually stupidly important. It's one of the building blocks of actual addition, subtraction, division, and multiplication. I mean, I guess you could say that about literally every gate, but whatever. Anyways, we now need to take this NAND gate and hook it up to one of the 2 NOT, and hook them up to 2 NOT gates. And then we hook these inputs up to a chip and smush that into one. And then boom! We have the OR gate. Now you probably would have been able to infer what the NAND gate does. But what about the OR gate? Well, it looks like this. The OR gate, as long as one of its inputs is on or both, it will have its output on. The only time it ever doesn't have its output on is when both its inputs are off. Every other state causes the output to be on. Anyways, this is still not relevant. We still have to go up another level of abstraction. It's now time for the exclusive OR gate. So let's take the OR gate and a singular NAND gate and hook both of their inputs up to these 2 inputs. That makes a little cross-wiring thing that kind of looks like this. And now take its two inputs and hook them up to an AND gate, and slap its output on the output of our chip, and then smush it together, and boom, the XOR gate. Now, how is this important? Well, it's like this. If we take our table and look at how the binary addition works, it's like this: 0 plus 0 equals 0. That makes sense. 1 plus 0 also equals 1. Same with 0 plus 1 also equals 1. But now, what about 1 plus 1? What we discussed earlier. This equals 1, 0. What does this mean in the binary world? It is now time for us to discuss carry and output. So when I was talking about carrying the thing over to the other thing, well, that has its own dedicated output on special little adding chips, like these little things. It's time for us to make the half adder. So let's take an XOR gate and an AND gate, wire them up like the same XOR gate that we made earlier, and wire their outputs up. And if you look at the table of what this thing does, it's identical to our table earlier. 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, and 1 plus 1 equals 1, 0. Now, that's great and all, but how is this important? Well, if we stick two of these together by wiring their outputs correctly and sprinkling in an OR gate for carry, we now have a full adder, which lets us add two numbers. Now, you may be saying to yourself, what's the point of all this stuff? I could just do calculations by hand. The point is, you just tricked electrons into doing math. They can do it a few billion times faster than you ever could. Hello. If you liked what you saw in this video, I'd recommend you to subscribe and like, because this took me a very long time. Those are my only reasons, by the way. Bye.